you would expect that they get broader, okay? And the idea is this. If you were to take, that's after, say, 1 photon absorption, okay? And this is a very simple argument, okay? This would be still the energy axis. After 1 photon absorption, you can imagine 2 photon is starting from this level. So you would go with a photon like that, right? Except that has some distribution too, because there's some bandwidth for that photon. You go from up here, there's some bandwidth for that photon. You go from over here, there's some bandwidth for that one. Okay? So the total peak over here would be the sum of all of those. Okay? And again, this neglects interference effects and perturbation theory and you know, all complications like that. The dipole, like I said, it's a very simple argument. This peak then, the sum of all of those, ends up being the convolution of this peak, if it's n photon, with the laser bandwidth, the power spectrum, which means that the width and frequency, or in energy, of the n peak goes like square root of n if they're Gaussians, of the original. Okay? So they get a little bit broader, and again, that very simple picture. So as you go higher, these will get slightly broader. Okay? What else could we say? Well, we want to look for C phase effects, right? So we're going to have more and more peaks out here. They might get a little bit wider, still be spaced by 1 photon. Okay? Where would you look for C phase effects? What C phase effect would you look for first in this spectrum?
Between different parities.
Between different parities. So this would be odd and this would be even, right? So these would be opposite parities. And so the overlap there would certainly show a C phase effect. Would it show it in the spectrum? This is the energy spectrum, right? Which means it's the yield. So the interference of different parities gives us control over what? Direction. So there will be C phase effects in here, but you would have to look at, say, the momentum distribution to see it. Okay? But that would tell you what energies to look at. Okay? But so this would be in the direction. Okay? And of course it would be in all of these spots.
Do you see more at higher photon numbers?
And as long as this kind of an idea holds at least, and these get broader, then the overlap would get bigger, so yeah, you would expect to see bigger effects at higher photon numbers. Okay? What else? How would we see C phase effects, or where would we see C phase effects in this picture, if they were there? Again, this is the yield, right? So which parities interfere? The same. So it would have to be this guy with this guy, right? So it would be the overlap of those two, which I didn't even draw in here because they're so narrow. Okay? We would have to get to much broader pulses. Again, it's the same picture I drew, which is exactly the point. It doesn't matter what the system is. It could be nuclei and H2+, it could be electrons and ionization. Okay? Well, we would need to go to broader pulses such that we had, something like that. This guy would, overlap like that. Okay? Now, this says that we're saying this is roughly the bandwidth, so the full width half max of its power spectrum has to be comparable to a photon, right? So delta omega, approximately omega, can we actually do that? And transform limited pulses? How long is that pulse in time? Do you have any idea? Okay, so for Gaussians, and for most transform limited pulses, delta omega, maybe I should write this down. Delta omega, the bandwidth, over the photon is approximately let's see, the number, 1 over the number of cycles, up to a constant. I think for Gaussians, the constant's like 0.3 or something. Okay? So if you have a pulse that's 1 cycle long, roughly the bandwidth is going to be on the same order as the photon energy. Okay? And that's about as short as you're going to get. There's about 1 cycle. Okay? Again, up to factors of 0.3 or so. So getting things this broad, at least in a transform limited sense, will be a bit of a challenge. Okay? Again, unless we go to high photon numbers and things broaden, then you might see more yield control out of larger photon energies, or larger photon numbers, I should say. Okay? So, what C phase effects do we expect in single ionization, at least from this picture? Control, of course it depends on the pulse, right? But you can control direction and you know where to look for the energies. Again, as we come from low intensities. Okay? You know where to look and what to do to try to get control over the yields. But notice also, the control over the yield, where these overlap, is going to lie under one of your peaks. So it's going to be a modulation on a big signal. This directional control is a modulation on a small signal. So both have their challenges. Okay? What else? If we wanted to see anything besides the lowest order interference, we want to see, cosine phi in the direction is just these two interference. But in principle, 3 can interfere with 6 over here. Right? That would give you a delta n of 3. That would give you a frequency of 3. So you would see cosine 3 phi contributions in the C phase dependence. Okay? But then this would happen over that. That's a huge bandwidth, right? Or a really tiny effect. You could look for delta n of 4, frequencies of 4 for yields. That would be, say, 3 interfering with 7 over here. And you can see how unlikely those are. That's why all measurements today on C phase effects and asymmetry just look like cosine phi. Almost all measurements in yield just look like cosine 2 phi. Okay? Because getting to this other regime is really, really hard. Okay? So, again, in this kind of a picture, we have some answer to the first question. When the intensity goes higher, the picture gets more complicated because these peaks aren't quite as simple as this lowest order perturbation theory predicts. However, there's nothing wrong with the formulation, only in the way we draw our simple picture for it. Okay, C phase effects, even at high intensities, are still interference between, say, n and n plus 1 photons, or n and n plus 2 if you're looking at the yield. Okay, you would just have to have the corresponding picture, and it's hard to write that down a priori. Okay, but it doesn't change the fact that you would expect to see cosine phi for the asymmetry. Because that's just a simple outcome of all of this. Doesn't change the fact that you would expect to see cosine 2 phi for the yields. Okay? So what do you think? Having that discussion, what do you think, what observable would you look at first if you want to see C phase effects? Direction? Why direction? It's the lowest order, right? Because these guys interfering rather than those guys interfering. So yeah, one would expect to see directional effects before you see other effects. And in fact, that's what people have seen. They saw directional effects. There's many more measurements on directional effects than on yield effects. Which effect do you think is more interesting for the coherent control, say controlling chemical reactions? The yield. Okay? So if you were going to start out and you wanted to control the yield, would you pick C phase as your parameter to do it? I mean, at least to me, I'm not an experimentalist, but that looks like kind of a hard way to go. Okay? How about that last one? Can there be C phase effects in double ionization but not in single ionization? this connects with picture I drew last time. So instead of this kind of a picture, we really need, well, this is the picture for single ionization. Keep it in your mind because I want to draw the one for double. And I want to draw it high enough for everybody to see. So if you're going to do double ionization, remember we had this kind of picture, energy for electron 1, energy for electron 2. And in this case, you're going to get the multi-photon piece will look something like that. And again, I'm just sketching here. So this line is total energy, and this might be, say, n equals 3, n equals 4, n equals 5. Okay. So if you wanted to see CE phase effects in a direction, and it depends on what system we're looking at, whether that's possible, where would you look for them? What's that? Asymmetry, yeah, but where, do you have any guidance where you would look? What energies would you look at? In between, right? Because even in double ionization, if I absorb 3 photons, every photon changes the parity. I don't care how many fragments there are. Triple ionization, double ionization, triple dissociate, doesn't matter. Okay, you absorb a photon, you change the total parity. Okay? So if you want to change the directionality, if you want to control the directionality, this would be odd parity, for instance, even parity, odd parity. If you superpose even and odd parity, that gives you control over directionality. That's in this region, right? Or this one, or the next one, or the next one. So those would be the energies you would look at. Okay? So if you can make cuts here and focus on those parts. Okay. Could you see those directional effects before you see them in single ionization, do you think? I mean, if I were to draw an energy scale, and let's say here's my ground state, and I won't say 0 energy. And I'm going to need 2 thresholds. I'm going to need single ionization threshold and a double ionization threshold. So I would have 2 lines here. So should the single ionization threshold be above or below double? Below. So single ionization is here, double might be over there. Which one takes more photons to get to? Double. And again, if there's something to this argument, then the more photons you absorb, the wider the peaks get, right? So you suppose there might be a possibility for CE phase effects in double ionization before single? Again, now with some caveats. You know, that simple picture has to apply. You have to be low enough intensities. So for the whole picture to sort of work in the simple way that I draw. Okay? But we haven't, have we used anything for a specific system? I didn't even tell you what system I was talking about. Okay? So that's, again, to me, that's the advantage. You can make arguments based on dipole selection rules, symmetries, energies, things like that. Yeah?
So, of course, atoms have this parity, and diatomic molecules, but
All molecules have it.
really,
Every system that interacts by pairwise central forces has eigenstates of parity.
CL?
Yes, absolutely. Every molecule, every system that interacts through pairwise central forces has eigenstates of parity. So, you know, when people talk about, I mean, this is a common misconception that molecules have permanent dipole moments. They do not, unless there's an external field. Then the external field mixes eigenstates of different parity that are close together, form a Stark state. That's how you get the dipole. That's how you see dipoles. Okay? So they have eigenstates of parity. Now, they may not always be the most convenient basis. I'll grant you that. Okay? But guaranteed they have it. Okay? If you have any molecule you want to pick, put it in the universe with nothing else, no external fields, nothing else, eigenstates of parity. This is it's a pretty simple proof, because if you can show that the parity operator commutes with that Hamiltonian for any system with only pairwise central forces. Okay? Yeah,
So I follow and agree with these arguments you presented, but it seems like competing ionization pathways for double ionization would really make this hard to see.
what do you mean? What other kind of pathway do you mean?
Well, I suppose I guess it depends on the pulse, but which, for instance, which electrons ionize first or...
It doesn't matter. It absolutely doesn't matter. That's the point. The intermediate states don't matter, right? Because you have a system, you have initial state, you have final state, some number of photons get you from one to the other. The intermediate states don't matter. So this would assume that your state resolves. So if you double ionize but you leave a core behind, right? Then you make this picture for each core state left behind. Okay? If you had a different core state left behind, you would have a similar picture, but it would be shifted. Okay? And that would be complicated. So using this depends on a state selectivity that you may not have an experiment, but you can use this to use this kind of idea to make a prediction for each core state, and then imagine what their superposition would look like. Okay? Do you have a question?
You mentioned pairwise, right?
Yes. What's that?
Amplified.
Pairwise interactions?
Pairwise.
Central interactions. Coulomb interaction. Right? The Coulomb interaction, which describes all our molecules,
Right.
only depends on the distance between the particles. So that's a two-body central force. Okay? And you can see then why parity commutes with it, because if you change all those vectors to their minus, then those magnitudes don't change, right? Okay. So maybe you're getting the idea a little bit better. Are there any questions? Another question. Okay.
So you have a C phase,
Yeah.
and in different C phases, they do different peak intensity for a single pulse.
No, the peak intensity is the same because you have the same envelope.
But I
You can think about the instantaneous field maybe being different, but intensity is a time average quantity, right?
but the atoms stay in the field, not that.
They do. I can show you the equation. There. Right? This is exact. And that's just the envelope. So the atoms see the field or the envelope? What's more important?
But the atom is not real.
It's not? Can I write the field as a carrier envelope in the carrier envelope representation?
Yes.
Yes. Okay. But again, see, the point is, all these are exact steps, right? No mathematical question there. This is carrier envelope, and it's the envelope that matters in this equation. You get all the C phase dependence, which means moving that peak field underneath that envelope. You get that information from this superposition. Okay? And that's the point here, is we're in the spectral domain, not the time domain. So there are no fields anymore. We don't talk about the instantaneous field in this picture. Okay? We're talking about the spectral content. Okay? We're talking about the spectrum. So it's a very different picture than most people think of CE phase effects. And as I showed you last time, you can make predictions here that you wouldn't make if you were only thinking of the field. Okay? And I don't have the picture here, but I showed you last time. I posed the question, what's more important for seeing CE phase effects? Is it the pulse duration, or is it the bandwidth of the laser pulse? Well, again, if we have, maybe I'll use it here. Did I really say anything about pulse duration in this picture? No, only in the sense that I sort of gave you the idea that these are transform limited pulses. But if they aren't transform limited, then I'm not saying anything about the pulse length in these pictures, okay? What I'm saying is, what's the spectral content, what's the power spectrum? And so to see CE phase effects, you just need the power spectrum of the pulses to overlap. The power spectrum, sorry, the spectral peaks to overlap, so you need the power spectrum to be broad enough. And I showed you numerical examples that supported that. I showed you experimental examples that supported that. Okay? So that, we did, my experimental colleagues and Itzick's group at K-State, they chirped something with 5 femtosecond transform limited pulse out to 20 femtoseconds. Okay? 20 femtoseconds is, well, 2.5 femtosecond cycles is how many cycles? Quite a few. And they still saw C phase effects. Okay? Which, in most, if you're thinking in terms of just the field, you would not expect that. Okay? So yeah, you've identified exactly the key difference between this picture and the way people normally think about this. Yeah.
So I didn't understand why even an atom is possible for every system, because if you have molecule with two centers, and you look at the ionization, you have one electron with two centers, there are no central.
No, this is the total parity of the system. It's not the parity of just the electron, it's the total parity of the system. That's what has to change when you absorb a photon, is the total parity of the system. Okay? You can break it down if you want. You can take that further and talk about if you have symmetry quantum numbers for the electronic part alone, how those would change under a dipole. But that's not the parity that really changes when you absorb a photon, it's the total parity of the system. Okay? And every molecule is, the Hamiltonian is just a sum of the electron-nuclear interactions and the electron-electron interactions and the nuclear-nuclear Coulomb interactions, all central forces. So parity eigenstates. Okay? But I mean, you can get into those details. I mean, in a sense that, from this point of view, those are details. Okay?
Well, I'm just wondering if they
Yeah.
are, because let's take the ground state of the system. Start easy with the ground state of hydrogen.
Okay. Hydrogen atom even.
Hydrogen atom, right?
Okay.
That's what I meant.
Yes.
Okay. What would you say is the parity eigenvalue of that system?
It's even parity.
You didn't even hesitate.
Yes.
Now, let's take something that's a little bit more complicated. Choose your molecule. I mean, I would choose the diatomic where the two nuclei are not the same.
Okay.
CO.
CO.
It's
Okay.
still, it's still, by the way, it's still closed shell.
Sure.
Okay. Even though ground state parity is
Ground state of the system?
Yeah, ground state, in the ground state, what's the parity?
To be honest, I don't know in that
Yeah.
case. It's even or odd.
Exactly. Exactly. In other words, it has two degenerate ground states. Even or odd. So.
No, I don't think so.
Is that right?
I don't think so. Once you include all the nuclear pieces, I don't think that's true. I don't think that's true. Now, they might be close. I would be very surprised if they're exactly degenerate. The electronic part, yeah, I mean, if you have pi states, for instance, or something like that, yeah.
And also in many value system, there are no even and odd. It's so that you can have three even and
True.
so
Well, is that true?
sometimes
Yeah, probably. Yeah.
sometimes you cannot use this argument.
Oh, but you can, because, you know, you have the even parity states, you have the odd parity states, you absorb a photon, you go, every time you absorb a photon, and that's what I'm drawing, you have to change parity. I don't care what the states of the system, if they're accessible or not, that's the dipole part, right? If there's no dipole to get to this one, maybe this one is suppressed, right? But this is one photon, that's another photon, just by energy. Then guaranteed, this is one parity, that's the next parity, that's another parity. Now, there's a complication of molecules that hasn't been mentioned, and that is molecules usually come in a thermal distribution. Okay? That thermal distribution doesn't care about parity, it only cares about energies. So your CO example might be, the ground state might be even, and then first excited odd and so on. but it's going to come in an incoherent superposition of those, a thermal distribution of those determined by the temperature. Okay? And all of that will come in here, but I can use these arguments to argue what happens with that even parity ground state, with the odd parity excited state, and then think about taking the thermal thermal average of the outcome. Okay?
I think
Yeah.
it is safe to say that there are no molecules we know which spontaneously break symmetry. In other words, exist in a superposition in the ground state, in the superposition of odd and even parity states.
In the total parity, look, I'm not a molecular physicist either, so I certainly can't say that. I'm just saying from a fundamental point of
I
view.
think this is safe to say.
However, in ground states, many of them have even and odd parity states close enough
Yeah.
that even small external fields, the environment of a liquid, makes them polar. That means that they have a dipole. That means that you've superposed even and odd parity states. Because what happens when you superimpose even and odd parity? You get directionality, right? Just like we talked about. And that a dipole is directionality. So, yeah. Other questions? Do we have time for more questions?
Well, you're the last speaker, you have as much time.
That's true. We're at lunch, right?
I don't know when the lunch is served, but we have time.
Okay. Well, I wanted to make at least one more point. Tell me when I should stop. That was the other point I wanted to make. I realize actually I have 2 points I want to make. It'll be 3 in a second. Just hold on. So, as I told you, we can write these observables. In this case, I just wrote the momentum distribution. It's a Fourier series. So I just rearranged the series I showed you before so that the C phase dependence is clearly in a Fourier series form. So this whole quantity will give you the amplitude of that Fourier component. But that means I can take an experimental spectrum like these, which were taken again by my experimental colleagues at K-State and the NITSICS group. Okay, I should write down what this is so it's clear. So this particular experiment is H2 plus a strong field goes to H plus H star plus, no, that's right, just H plus H star. Okay? Okay? And so what's measured here is the asymmetry of those, because H star, an excited state of H, is distinguishable from H. So you can measure the relative momentum distribution of those, and you can look at their asymmetry, the probability up and the probability down. So this picture is shows the density plot of this asymmetry, normalized asymmetry, as a function of C phase. So that's the C phase divided by pi. So this is up to 4 pi here. This axis is the kinetic energy release, the relative energy of those two fragments. Okay, and you can see that there's, the scale up here for the normalized asymmetry is minus 0.2 to 0.2. And you can see there's clear directionality changes as you change the C phase. Okay? But I told you, this is a Fourier series, so you can take the Fourier transform of that. Go to n space, okay, or delta n space. So, what you see, again, this is KER, so they did this for every KER slice. You see this strong line at 1 phi. Okay? That means it's delta n of 1 or minus 1. So that's a cosine phi contribution to the asymmetry. That's what we said would be the dominant one, right? That's the interference between neighboring photon peaks. Okay? But you also see some noise, but you also see this fairly strong peak over here at delta n of 3. That's the interference of pathways that differ by 3 photons in their absorption. Okay? And if you look at this inset here, that's a cut. Let's see, I have to get close to read this. That one is, you can see maybe 2 lines right here. That's this peak, right? That's this peak. So if you just take and then along there, you can see that's the trace. That's the C phase dependence along this way. Clearly not cosine phi. There's a clear higher frequency